Hi, my name's Gavin. I'm with Group 10. We are Ray Tracing. My teammates are Pedro Contipelli, Tanner Fleming, Christopher Gray, and Diego Rodrigues. To introduce the project, we are studying specifically multi-threaded ray tracing. Ray tracing generally is a computer graphics technique where you can define objects in 3D space, whether they be spheres, cubes, or other random shapes. Take a viewport, whether it be like a point of view camera, and from that viewport send lines out into 3D space, see which objects appear in front where the intersection points are, and from that you can discern a graphical image that the user can see. The most primitive form of this is called ray casting. It's a 2D implementation, most commonly found in Doom and Wolfenstein, using 2D objects, almost exclusively cubes, and a thin FOV. The more modern form is called ray tracing. This uses 3D space, 3D objects like spheres and cubes or other free-handed 3D meshes, and from that you can discern reflections, you can check shadows, you can check lighting, you can check a lot of different things using ray tracing. The main roadblock with ray tracing is going to be processing power, not algorithms. The big thing is processing power because it takes a lot of calculations to find these things and make it look realistic. We've had algorithms for a very, very long time, since the inception of ray tracing, which we'll discuss on the next slide. Ray tracing first became a thing in the late 1970s. And during that time, algorithms were defined. There were ways to generate ray trace 3D graphics even back then. It just took a long, long time. Even decades later, in 2006, when Pixar's Cars was created, it took multiple hours to render a single frame of the film, leading to days and months for the entire hour-and-a-half long film. In 2009, there was a Quake Wars demo with ray tracing technology by Intel, and this was in the days where we didn't even have dedicated graphics processing units. We only had the Intel CPU. It was real time, but it was very low poly and very low resolution, so not very high quality graphics, but it still was a proof of concept that ray tracing was possible in popular media like video games. In 2013, NVIDIA Research published a paper on global illumination using the GTX 770 hardware. This hardware is less powerful than a PlayStation 4, so nowadays it's relatively easy to get hardware of that caliber. This global illumination was essentially taking a single light source like a simulated sun and using ray tracing to light the entire environment from that one source. In 2017, we had fully dynamic lighting, meaning that calculations would happen live and you can move objects around, whether that be objects in space or the light source itself, and you would have a rendering time of 3.9 milliseconds for every frame. So it's very near real-time ray tracing in 2017. This was using the Intel Core i7-3770K CPU, 32 gigs of RAM, and an NVIDIA Titan X Pascal GPU. So for the time, it was top-of-the-line hardware, but it was possible. In 2018, NVIDIA published their Reflections demonstration. It was a Star Wars-themed demonstration using their RTX series graphics cards to generate hype for the new generation of graphics processors. And most recently, in 2022, late March this year, NVIDIA released the GeForce RTX 3090 Ti, which is the most advanced graphics processing unit that we have in the consumer market to date. Next slide.
So before we get to ray tracing, we can go back to the basics and see what is actually a ray, right? So in this example we have over here, we have pretty much an origin point and a direction. That's pretty much a ray. It's just pretty much a point in space, in this case an X and Y, and a direction, as you can see, it's the arrow. Next slide, please. And as you can see over here, the whole point that we're going to be doing this application, we're going to be throwing these rays at objects. And this is the most simple example we can find, just getting a point called origin and we're going to be throwing a ray towards that object over there. And what are we going to be seeing is like sometimes there are going to be things in between, and that's when we're going to be casting shadows in our views, and which you're going to be seeing in the next slide. So now we can actually talk about ray tracing, right? So like if think of yourself playing like a video game, you have your computer screen, and in that computer screen you have like a set of pixels, right? So what the camera in this game is going to be doing is going to be throwing these rays at that scene object, and those rays are going to be going through those pixels, it's going to be hitting that scene object, which then are going to be, the rays are going to be thrown to the light source. So if you see the first example over there, the view ray is going to be throwing itself to the scene object, going through that pixel like that you see on the screen, and then it's going to be referring itself to the light. So that's going to indicate that it's probably going to be a bright spot. Since it's so close to the light, there's nothing in between. But if you see in contrast the ray below it, it's throwing itself to under the object. And when it's going to be going back to the light source, it's going to be casting a shadow because there's a scene object in between that and the light source. And that can be useful for like plenty of other things as well. Like let's say if you have like a mirror or some sort of that ray is going to be bouncing off the mirror and hitting maybe another object and so on and so forth, as you're going to be seeing in the next slide. So over here, we have a glass ball. It's no longer like a smooth ball that we had before. So, and the camera is just the eyeball over there in the example. The ray is going to be throwing itself to the surface of the glass ball, and then immediately it's going to be referring to the sun in this case, or the light source of the scene. And after that, you can probably guess that it's probably going to be a brighter side of the ball. But after that, the ray is going to be going through the glass ball, hitting multiple points in the glass ball because, as you know, it's going to be reflective in there. But all those points are going to be referring back to the light source. And finally, it's going to be throwing itself to the diffuse box. And what you notice over here is a shadow. And as we saw before, because that shadow is caused because that final ray that's going to be referring itself to the light source is going to be stopped by another wall, and it's going to be causing a shadow in the scene. So next slide. As you can see over here, like that's pretty much, this isn't exactly what the example was like, but you can have an idea of what it's going to happen if like a ray goes through one of those light sources. You see all this reflection going on and all those textures and all the beautiful scenery, and it's going to give you pretty much what you're used to seeing in movies today, like that require animation, or in state-of-the-art video games.
Okay, so I'm going to be talking about the more advanced math, linear algebra, and other techniques that we're using for the actual implementation of ray tracing. To begin with, at its core, you really have to understand the physics of actual light rays in the real world, because all ray tracing is based on actual physics. So at its core, light can be either reflected, refracted, or absorbed. I'll get a little bit more into what each of those means. But essentially, which of these interactions occurs and how often and how much, all of that is governed by both an object's material and its geometry. However, in the case of our project, we were only working on rendering spheres just because of time limitations and scope. But all of these techniques could be applied to really any general scene that you would like to ray trace. Again, into our first type of material would be a diffuse object, which you can think of your regular everyday ball that you would find in a ball pit that has some color. Essentially, the way that the physics of that material will work is because the surface is actually slightly rough. The direction of light is randomized when it reflects off of its surface, and some of the light is actually absorbed according to how dark the surface is, which is why you may see more reflected light off a sheet of paper than a dark object. So we have a scaling factor in the code which can essentially reduce the amount of light that's being reflected. That's the absorption factor. To calculate this random bounce ray off a diffuse object, we're actually going to use some math So if you can follow along with the picture here, this would be the incoming ray of light R. We're going to find the tangent unit radius sphere on the same side as the ray, which would be, obviously outside the sphere here. And this is actually not as trivial as you may think to just find a random reflection, because all of this must be oriented in 3D space. And the distribution of randomness actually matters a lot, because you might get really unrealistic looking reflections. So what we'd like to do is pick a random point inside the sphere. And the method for doing that is called rejection sampling, which essentially just means we can generate 3 random numbers with your standard RNG. And so that would be maybe in the unit cube. However, some of those points may actually lie outside of the sphere. So we're just going to reject any points that lie outside the sphere and wait until we pick randomly a point that does lie inside the sphere. That's why it's called rejection sampling. And we are going to then, once we've found that tangent point, send a ray from the hit point P to the random point S. And that's going to be the actual direction of where that light is going to bounce randomly off a diffuse object. You can see a little bit more clearly why that happens here on the bottom. So this would be your diffuse object, this diagram B. As light hits a rough surface, it can bounce at really any angle due to the actual nature of the material. However, not all objects behave like this. One that everyone knows is a mirror. A mirror is a very smooth surface, and that gives it the ability to reflect light at a perfect perpendicular angle to the direction that it came in. So we can also calculate how light would reflect off a mirror object. And we can use some vector math to calculate that reflection, which is what this formula is here. I won't do too in-depth of an explanation of that, but essentially we can use this B vector and kind of imagine multiplying this ray of light down into the object and then adding back in the vertical factor that it was lost by using the norm, which is just a unit vector in the upwards direction. So to calculate this red vector out here, which is our reflection, which is the thing that we're looking for. So all it takes is adding up all of these vectors to get that. Secondly, for smooth metals, if you think of maybe a piece of aluminum foil, it's not actually a perfect mirror. You can see your reflection, but there is some fuzziness there. And so we can actually add that in as a coefficient, as a factor, by simply adding in a bit of random noise. We can use, again, the same rejection sampling technique around the direction of where the actual reflected vector is. And that will give us a bit of noise to make the reflection off of a smooth metal surface look more realistic. And so here in the bottom pictured, you can actually see what this is doing in terms of our actual ray tracing. On the left, this would just be a perfectly smooth metal mirror. You can see that everything is nice and crisp. Versus here, we've added in some of that random noise fuzziness factor. And you can see how it's a little bit more blurry and a little bit more what you would expect from a real metal object in the real world. And our last material that we implemented is dielectric, which just represents any kind of clear material such that light can actually pass through, such as water, glass, and diamonds. The actual physics of what happens when a light ray hits a dielectric surface in the real world is that it splits into one reflected ray and one refracted ray. What a refracted ray is essentially the ray that goes through the surface. which that direction can be calculated using Snell's law. And the way that this works is essentially every material has some index of refraction, which is this term here, which essentially specifies how much the light will bend upon entering that surface. Because if you've ever seen maybe like a straw in a cup of water, you notice that it looks like the straw is bending when really it isn't. That's actually just the physical nature of refraction. It doesn't continue in the exact same direction. It's shifted by some angle. And so you can use Snell's law from the real world to calculate the direction of that vector. And the last note on implementation is that to keep things simple, we can actually approximate this interaction without having to calculate both the reflected and refracted ray every single time, because that would give us, exponential computation with having multiple reflections and refractions all over the place. We can keep things linear and still get a good approximation by simply randomly choosing one of the rays, either the reflection or the refraction, to calculate for each interaction. And that will still give us a realistic looking picture for our project without having to simulate, this super long actual process of exponential light calculation. Here on the top, you can see a picture of what a filled in glass sphere would look like. You can see this lensing effect where it's actually reflecting the bottom surface of the ground on the top of the sphere and the sky on the bottom of the sphere, which is really what you would get if you are looking through a fully glass sphere in the real world. However, we're just not used to seeing that very often, so it may look a little bit weird. But in lenses and whatnot, this is an effect that you do see. Here is a little bit harder to see. This is a hollow glass sphere. So we're actually getting only one entry and exit point of the refracted rays with Snell's law. So you can see that the light is not completely, upside down reflected. But there is still a little bit of distortion, and you can see kind of the outline of the glass. But it looks more like looking into a window than looking into a lens that's completely out of focus. And the last thing, this is, we've covered all the materials. We'd also like to actually have an oriented camera in our 3D scene. For this, we're going to need to specify a couple of points in the 3D space. We will need one point to represent where the camera is positioned and actually looking from. So we can call that in our code just the look from point. We will need another point which will help us form this ray or vector, which tells us where we're looking at, so what direction from the look from point. And we actually will need a single more vector, which is called V up, which will help us specify the roll, which is kind of like tilting your head to the left or to the right, because just using these 2 points is actually not enough to fully determine what the picture will look like. We need the full 3D basis vectors to get the right exact orientation and rotation. But using these 3 vectors, it is exactly enough. And in the next slide, you'll see the effects of being able to orient the camera anywhere in 3D space. So here we took that same scene from before, but we're now looking from some point that's slightly above and diagonal to the scene. And the look to is at the actual objects with very minimal roll or rotation. And here is just a zoomed in version of the same thing so that you can see that the light is actually still calculated correctly from really any position or orientation of camera.
As for the implementation itself, we created a C++ program that would render a PPM file or portable pixmap file, which is just a very simple image format that we fill in by generating pixels one at a time from top to bottom and left to right. The program is comprised of a few classes, such as a vector class and a color class, which have their own functions associated with them to perform some of the mathematics that's been previously mentioned, as well as a camera class that stores the look from and the look to points, as well as the aperture and other things, as well as a hittable class, which just represents any object in a scene that can be hit, in this case, spheres. A scene is a hittable list, which is just a list of these hittable objects, and the light rays are represented with a ray class. Each hittable object has a material associated with it, and each material has some sort of reflection behavior as previously discussed. And the program simply goes, again, a pixel at a time and shoots a light ray out to the spot in the pixel, and then determines which hittable object was closest to that ray, then reflects, and then repeats recursively to a specified depth. This process takes quite a while, as there can be many reflections and light rays bouncing off of many objects. And you don't do one light ray per pixel, you do many light rays per pixel, and you get high run times with this. So next slide. So to cut down on that, we can use multi-threading. So the pixels themselves can be generated independent of other pixels in the scene. So each thread can take a block of pixels and compute the RGB values for that block, and then return all that to the main thread, which will then create the image or piece together the image. So in the code on the right at the top, just creating an array of our threads in the streams that they'll put the RGB data into. And then each thread will be given the render task, and it'll be passed all the information, so such as the camera and the world, the height and width of the image, and the block that it will be rendering. All those threads will then come together, and then the streams of RGB pixel data will then be delivered to the output stream, which will then be redirected into a PPM file. This helps cut down on runtime significantly, as each thread can work on its own set of pixels independent of other threads. So next slide. The main challenge involves distributing the work evenly. As mentioned, some pixels will hit objects, and that light ray will bounce off and hit another object, and then you have to keep recursively calculating the light ray. So some pixels, however, will not hit any object, such as rays that are targeted at the sky. So sometimes some pixels take way less work than others, and it's not necessarily always clear which sections will take more work, because objects could be anywhere in the scene. So to load balance, there's if you have too many pixels per assigned task, such as just simply breaking down the scene into blocks and giving each thread a block, some blocks will finish significantly quicker than others, and they will be left waiting and not being put to use. But if you went with the opposite approach and assigned one pixel at a time, there's a lot of overhead with actually giving a thread a pixel, and then all the independence part is broken, and then you have to synchronize which pixel is next. So that ends up actually slowing it down. An approach somewhere in the middle is to assign some amount of scan lines and this can be dependent on the image, and it's tricky to, there really is no magic number that you can use. One way to implement some sort of task system would be with thread pools, where when a thread is finished with its, in this case, set of scan lines, it could be given another set of scan lines. However, this is not in the default C++ library and would have to be implemented ourselves, and thread pools aren't a trivial thing to implement.
Now let's get into the numbers. So on the running of the non-multi-threaded implementation, we saw a runtime of 88.98 minutes, which is not ideal. It's a pretty long time. Once we implemented our multi-threading solution, we got that number down to 20.66 minutes. That's a 76% improvement. That's pretty good in terms of improvements on a program you can make. 76% is a nice amount of time to save. Next slide. For the future of this project, we'd obviously like to implement the load balancing, like we said in the challenges section. Another thing we'd like to see done is some more active renderings rather than just the static rendering that we did of the orbs or the spheres. Something more active, something you could interact with, possibly a small game. Next slide. So what we learned from this project is the power of multi-threading, especially when it comes to really high workload programs like ray tracing. There's so many different algorithms you have to run on each individual pixel that the amount of processing power you need just escalates so quickly. You need to have a proper implementation in your program to utilize all that power as efficiently as possible. And really this class helped us learn those fundamentals to apply to these programs and implement this solution that cut down our runtime so much. Another thing we learned doing this project is that this is a problem that is definitely still ongoing. Even the industry leaders, NVIDIA, in this field are still improving on it and trying to find new ways to maximize hardware and software to cut down on time. So we're very happy with our 76% improvement in time. And don't forget to like, comment, and subscribe.